Hi, Honors Chemistry students. Make sure you have a copy of the note sheet so you can follow along. Let's take a look at some of the information on the first page. I would advise that you pause this video for a minute and read through. Hopefully this looks pretty familiar to you. You've had some practice with similar problems before. You're finding the percent composition of an element in the compound. So for example, if we're doing sulfuric acid, which is H2SO4, and now you know how to name acids, then you would want to find the percent composition of each element, unless you were told just to find one of them. To find the percent composition of hydrogen, you put the mass of hydrogen in the numerator. There are two of them because the chemical formula has two hydrogens in it. And then you put the molar mass of the whole compound in the denominator. And that'll be the same for all of them. Remember that percent composition is part over whole times 100. And that part over whole times 100 was true even back in September when we were talking about sand, salt, and iron. But here we're finding the theoretical percent composition for this compound, sulfuric acid. Notice also that all the percents are going to have to add up to 100. Again, pause here for a second and see if you can find the percent composition of carbon and oxygen in carbon dioxide. Okay, so first you want to calculate the molar mass of your compound. Because it's carbon dioxide, it's 1 carbon at 12.01 grams and 2 oxygens at 16 grams. So we add those up and you get 44.01. The units technically are grams per 1 mole. So sometimes you see that listed as grams/mole. We know that that can be used as a mole conversion. And to find the percent of carbon, then you're going to take the mass of just the carbon over the mass of the whole thing times 100. And we're counting sig figs here, so you get 4 sig figs. That's 2 places after the decimal for this compound. Now try to calculate the percent oxygen. One way to do this is to put the mass of oxygen over the mass of the whole thing times 100. That'll give you 72.71%. Maybe you can think of another way to do this. Only have 2 elements in a compound. The other way is to just subtract the first one from 100. The 2% together have to add up to 100%, just like the 3% in H2SO4 have to add up to 100. Pause to do problem 2 and then check your answers after you've completed it. Those are the 3% that you should get for the percent of carbon, the percent of hydrogen, and the percent of oxygen in lactic acid. Being able to find this information when you have a sample of a compound in a lab is pretty easy. You wouldn't use the elements' masses on the periodic table, but you could collect lab data. And using that lab data, there's a fairly easy way to derive a compound's empirical formula. So we have to take a second and talk about what an empirical formula is. It's the lowest mole ratio of elements in a compound, which is different from what the actual formula is, or the molecular formula. It's probably easiest seen through examples. So acetylene, for example, the molecule itself is C2H2. If you drew the Lewis structure, if you actually saw the molecule, it'd be 2 carbons and 2 hydrogens. The empirical formula has the same ratio between the atoms. In this case, this is a 2:2 ratio. Well, that ratio in kind of lowest form would be 1:1. And so the empirical formula is just C1H1. We just don't write the ones there. Same thing with benzene. Benzene is C6H6, and its formula kind of in lowest terms is also just CH. So acetylene and benzene share the same empirical formula. Ammonia is a little different. Its empirical formula and molecular formula are the same because the ratio between the atoms is 1:3, and that is the lowest form of that ratio. So again, the empirical formula is the chemical formula kind of in lowest terms with the smallest whole number ratio between the atoms, but may not actually represent what the molecule looks like in its actual form. So there's a good graphic on the previous page that goes through how to solve one of these problems. And then up here on this page, there's kind of, I don't know, it's not a great rhyme, but it's kind of a rhyme to help you remember how to solve these problems. But basically what we're trying to do is take a percent by mass and turn it into an empirical formula. So we're going to go through those steps in an example. So in this first example, the percent by mass of iron is given in a compound. The percent by mass of oxygen is not given, but we can find it relatively easily. Because the compound's only made of 2 elements, so they have to add up to 100. So we take 100 minus the 69.94, and we get the percent by mass of oxygen has to be 30.06. So we're going to follow our steps, and we're going to take the percent and change it into a mass. Basically, we're going to pretend that we have 100 grams, and just if you have 100 grams and 69.94% of it is iron, then it's 69.94 grams of iron. Okay, so that first step is pretty darn easy. All the steps actually in empirical formula problems are pretty easy. The next step we're going to do is we're going to take the masses that we have and just convert them into moles. Okay, so just a quick mole conversion there, and I'm not actually paying attention to significant figures. I'm just going to keep like 4-ish places after the decimal. Better to keep more than less. Eventually we're going to round, but we're going to kind of wait until the end. The other thing is oxygen generally is diatomic, but keep in mind that this oxygen is actually a part of a chemical formula that includes iron. So its subscript might be 1, 2, 3, we don't know yet. So in other words, for empirical formula problems, you get to ignore significant figures in diatomics, which should be pretty exciting. Okay, the next step, number 3, says divide by small. So we're going to look at the numbers that we got from step number 2 and just find the smallest one and divide them all by that number. So the iron number of moles was the smallest one, and so we're going to divide everything by that number of moles. Okay, here is where we get to kind of round. If it's really darn close to a whole number, like 1.0001 or 0.9994, then just round to the nearest whole number. If you're really far from a whole number, but close to kind of like a fraction, an easy fraction, like a half or a quarter, then you can't round to a whole number. Leave it as that like simple fraction. So when I did this division, I got 1 and like 1.5. Now we're going to do the last step, step number 4, which is to multiply until you get a whole number. So we're going to multiply both of these by whatever it takes to get a whole number, which is generally going to be something pretty easy. You're going to multiply by 2 or 3, or you might even not have to multiply it. But so our answers here, we get 2 and 3, which means our chemical formula is Fe with a subscript 2 and O with a subscript 3. So let's kind of look at what we did here for a second. First, we were given that we're supposed to find a chemical formula, but we're just given percents. And so if you write that, like up here, that is not how we write chemical formulas. Those subscripts do not represent percents. So then we turned them into mass, but those subscripts do not represent mass either. Okay, so those subscripts do represent moles, and we know that from our mole unit, but they're not supposed to be weird numbers. They're supposed to be whole numbers. So now we have weird numbers, 1.2523 moles and 1.8778 moles, and we have to somehow turn them into a whole number ratio. The easiest way to take weird numbers and turn them into a whole number ratio is to make one of them 1. So pick the smallest one and make it 1, which was what we did here, and then make the other ones relative to that. So that's how we got Fe subscript 1, O subscript 1.5. But we can't have, that's a simpler ratio, but it's not a whole number ratio. So we said, well, heck, that's the same as Fe2O3. A 1 to 1.5 ratio is the same as 2 to 3, and chemical formulas just have to be written in a whole number ratio. You can't have a fraction. Okay, now I suggest pausing the video and trying number 2 based on what you have written for number 1 and see how far you can get on your own. Okay, here's step 1. You just take the percent, make it grams because we're pretending we have 100. Okay, now we did step 2. We converted all the grams to moles. Now we got to do step 3. Okay, when I divided them all by the smallest number of moles, I actually pretty much got whole numbers. Nothing was like 0.5 or 0.25. So I actually don't have to multiply them by anything to get our chemical formula, which is Hg subscript 1, which I don't have to write, S subscript 1, which I don't have to write, O4. So there is our empirical formula, the smallest whole number ratio between the atoms in this compound. Okay, you should be able to do number 3 on your own. If you got that as your answer, you're doing great. Okay, but remember we said the empirical formula and the actual molecule aren't necessarily exactly the same. So the one thing you need in order to go from the empirical formula to the actual molecular formula is the molar mass. And what you want to do is take the empirical formula and find the mass of the empirical formula. So we'll take 2 carbons, 12.01 grams, and 5 hydrogens, and we're going to add that up. So you'll find that 1 mole of the empirical formula weighs 29.07 grams. But it says that the actual molecular mass is 290 grams per mole. So there are a lot of molecular formulas that would have the empirical formula C2H5, right? You could double it, you could triple it, you could quadruple it. And what would happen to the molar mass if you did that is you would just take this whole thing and you'd have to like double it, or for this case, or triple it if you were going to do this one. And you can guess and check, but there's actually an easier way to do it. You can just do division and figure out how many times the empirical formula fits into the molecular formula, or division. In this case, it's 10, and it's always going to be a nice, easy whole number, in which case we know this number has to be 10. It has to be 10 times the empirical formula, so that's going to give you C20H50, which is this one. Okay, pause the video for a second and start number 5. Start by finding the empirical formula. Notice with this one that you actually have lab data. You have a mass of hydrogen and a mass of oxygen. You do not have to go to percents and then go back to mass. You can actually just start with those masses. So again, I just started with those masses and then converted them to moles. Now, if you went back and found percents with them and then did percent to mass, mass to mole, you would have gotten the same thing. That it looks like these are about in a 1-to-1 ratio. You can double check, divide them both by the smaller number, 0.4325. And again, I'm ignoring sig figs. I'm just keeping like 4-ish places after the decimal. Eventually, we're going to end up rounding. This one's pretty easily 1, and this one is really darn close to 1. So our empirical formula is going to be H subscript 1, O subscript 1. Now our last piece of information is that the molecular formula has a mass of 34 grams per mole. We know this does not have that mass, right? This is just 1.01 plus 16 gives us 17.01 grams per mole. But we do know that the molecular formula is going to be some multiple of this. So it could be H2O2, it could be H3O3. And the easiest way to do that, instead of guessing checking, is just taking 34 grams per mole and dividing it by 17.01 grams per mole to figure out how many times that fits into the other one. And you get 2, and maybe you can just see that these are always going to be like kind of simple whole numbers. So we know that our formula is actually H2O2, and that's our molecular formula. We've got our empirical formula here, and then our molecular formula here. The actual molecule looks like H2O2, but the smallest whole number ratio between the atoms is 1-to-1.